Hello everyone, my name is Eric Kirshner. I'm a junior at Penn State University studying meteorology and atmospheric science. And we're going to be looking at a case study from May 11th, 2024 in Western Maryland. This particular video was taken by Sean Bender on Facebook near Accident, Maryland, which is in northwest Garrett County. You can see a tornado dropping down the mountain there. You can see the large area rotation. And what made this storm very special was that it was unwarned by the National Weather Service. So the purpose of this case study is not to bash the National Weather Service or the Storm Prediction Center. They're excellent meteorologists, but this caught everybody off guard. The environment was really not indicative of tornadoes this day, so we're going to take a look at why. And another thing that made this event special was that the previous day, May 10th, 2024, we had the beautiful display of the Aurora Borealis across western Maryland. So technically, if you were in the right place at the right time, you could have saw the aurora on May 10th, went to bed, got up, and then chased tornadoes the next day, all in western Maryland. So a major shout out to Convective Chronicles. He had a video called A Guide to Cold Core Tornado Environments, and I heavily relied on this for this case study. So let's take a dive into the case study and see what was so special about this event. So this is the Storm Prediction Center outlook the morning of May 11th. And this just basically shows the areas of highest severe risk. And you can see that when you got up that morning, there was no severe weather really expected across western Maryland. The Storm Prediction Center had a general thunderstorm threat, which means basically, sub-severe thunderstorms. But as we went a little bit later, they did eventually put the level 1 out of 5 severe threat. But typically when you're under that marginal, you're only expecting 1 or 2 storms, definitely not an outbreak. And one thing that's really interesting was that there was no tornado risk expected that morning across southwest Pennsylvania, western Maryland. There was absolutely nothing. Yet we see that there were 15 tornado reports from southwest Pennsylvania into western Maryland, and there were 2 tornadoes in Garrett County, Maryland. Both were EF1 tornadoes. Neither of them did any injuries or deaths, but they did do some damage there. You can see estimated peak winds of 90 miles an hour, and both had a max width of about 75 yards and were on the ground for a couple miles. And the times of these tornadoes were just shy of 8 p.m., 7:55 p.m., and then also just after 8 p.m. So definitely a very interesting event. So let's dive into this event and see kind of what made this storm tick. So we're going to look at a paper called The Environment Characteristics Associated with Tornado Events Near Closed Cold Core 500 Millibar Lows. And it was done by Geyer and Davies, 2 meteorologists. And without getting too much into what a cold core system is, you can go to Convective Chronicles and get a much better analysis. Basically, this storm system had a lot of cold air at the top of it throughout the column. And that allowed for a lot of instability and some special dynamics that don't normally occur that allowed for even a very meager environment to produce tornadoes. And this is a diagram of what that special characteristics look like. One thing is basically you have basically at 500 millibar, which is just a pressure level, you have a closed low. And I'll show you what that means in a little bit. And also you have a surface low nearby. So you have a surface low nearby, and you can see that in the warm sector, you have a low pressure, you have a cold front extending down, you have your warm front extending out. That's just the classic structure of a low pressure system. The warm sector is really not that warm. You can see that the dew points, which is just basically a measure of moisture, are only in the low 50s, and technically you can have dew points even in the upper 40s with these cold core events, and you can still see tornadoes. Basically, with cold core systems, they take a little bit of moisture, a little bit of heat, but because of the very cold temperatures aloft, it allows for potential tornado development. So this is at 500 millibars, which is basically looking at a surface at constant pressure. And basically, we measure the height of air, and pressure decreases faster in cold air than warm air, and that helps us get a look at what the environment is. So this is on May 11th, and I can kind of show you here. So this is on May 11th here. We can kind of take this back here. Let me see. This is at 18Z, and you can see a couple things here. You can see as the day goes on, you see how up here, you see how this, because you can see the circle right there, that is a closed isobar, and that's what that closed low means. Basically, at 500 millibar, you have a closed area of low pressure. And if you also see right here, you can see this this red shading right there. That is negative 24 degrees Celsius. So this was early May. You have an intense area of cold air tucked in right under that 500 millibar low there. Now, if we go to the surface here, you can see we have this is at the surface looking at pressure. You can see we have a closed area of low pressure there across the Great Lakes. Now, I will say this is not a perfect cold core system because we'll see some things. This is more like a pseudo event. It was close to, but not quite what we see because if you go back to the schematic here, we see that where those lows are close to each other, you're going to see the area of tornadoes that kind of further over here to the east. But if we go back to our surface thing, you can see that our low pressure was kind of up in here. So one would think if you're looking at a classic tornado event, you would expect your tornadoes to kind of be further up here, not down here. So kind of one thing that makes this more of a pseudo event, but there's still some aspects, especially the intense cold air loft that allowed for tornado development. We'll get a little bit more into that. So another thing, if we go back to the schematic, we see that really in these cold core events, because you have that cold aloft, you really don't need that much moisture at the surface, and you need moisture to allow for storms and storm energy. And if you look here, this is a map kind of scaled for moisture and dew points. I believe this blue here is shading for dew points. You can see that especially that later that day, their dew points was very meager across there. In fact, there was actually very little dew points to work with at all. And we're going to take a look at the soutings there and kind of give a better idea. But you can see we had very little moisture to deal with. Now, one thing that we did have is that we look at shear, which is basically the turn of winds with height, and that basically allows this for rotating thunderstorms. We did have 30 knots of effective shear across the area that evening, so we had some shear to work with. There was a little bit of spin with height that basically if a storm could form, we could see storms to rotate. But 30 knots is at the minimal there. But this is another thing that was very interesting here. This is what's called 0 to 3 kilometer CAPE. And CAPE is basically convective available potential energy, which is basically the measure of how much energy a storm has here. And 0 to 3 kilometer CAPE basically measures how much storm energy is in the lowest levels of the atmosphere. You don't really need a lot of storm energy as long as it's if it's confined within the lower levels, so that any spin at the surface, right, if you have a boundary, you have some terrain interactions going on, if you have a lot of storm energy at the surface, it can basically cause a storm to just stretch whatever's there and bring it to the vertical. That's why all that cold air aloft, you had a lot of instability that was able to stretch what little spin you had at the surface. And you can see this is at 00Z there on actually May 12th. We go back, this is 23Z on May 11th. You can see we have a bullseye of 100 joules per kilogram of CAPE there in southwest Pennsylvania and western Maryland. So you think, interesting. And that's just a classic sign of a cold core event, is you have a good chunk of instability right at the surface because of that cold pocket aloft. So basically you had some shear to work with, and since you had instability at the surface, it was able to stretch into the vertical what instability you have. So if you kind of look at the atmosphere, let me see, I can kind of draw a picture here in a kind of a crude way. Let's say this is the surface of the Earth, and let's say you have a little bit of spin at the surface. You have a little bit of spin. I'll just kind of do it like this. You have a little bit of spin at the surface here, a little bit of shear. Now let's say you get a storm cloud to come over. Storm cloud. Well, it has rising motion, so it stretches that air into the vertical, and sure enough, you're able to get a rotating thunderstorm brought up into the vertical, and that allows for the storm to spin. I know that was drawing is not my strong suit, but that's kind of the whole overall principle. And another thing we're going to look at here is this is another product called LCL height, which basically how low are the clouds of a storm. And you can see this is 21Z, so that afternoon. You can see that LCLs across southwest Pennsylvania and western Maryland are very low. about 750 meters. And we'll kind of see what's important about that. So let's go back to this paper on cold core environments, and we can put together all that we just saw. Okay, so this is a table that basically contrasts cold core environments. So this is cold core environments here, cold core environments, with your typical supercells and tornadoes, your typical rotating thunderstorms. And one thing that you see here is that you're typically dealing with a lot less instability, a lot less storm energy than their storm counterparts right there. You can see, though, that your 0 to 3 kilometer cape is much higher than your typical storm event. Your 0 to 6 kilometer shear, which is basically how much turning of winds you have with height, is lower than your thing. And you see that in typical cold core environments, you're only dealing with 33 knots of shear. Sure enough, we have that. And look at this here, that you're looking at your LCL heights, which is basically how low are your storm clouds. You see they're much lower than your typical storm environments. So basically we see that our event's starting to shape up. It's not a perfect example, but it's looking pretty close to being a pseudo cold core environment right there. So basically, so now let's take a look at this here. So if you're watching this and you're probably like, okay, if you are familiar with storm terms, you're probably following along. Hopefully you're following along good. But for those that have not really seen all this, this has been a barrage of storm names and all that. So just feel free to ask any questions in the comments if you need to. But this kind of shows how complicated meteorologists, all the products we have to look at, and it's never quite a perfect world. And I'm also going to show another quite daunting thing. This is called a skew-T sounding and a hodograph. And this is a reanalysis sounding here. And you can see this was taken just east of Uniontown, Pennsylvania there at 21Z on May 11th. And there's a couple things we can notice right away. So over here, we'll focus on the left side right here. This is basically a visual representation of how much instability you have in the atmosphere. And one thing you can see right now is that you do have some instability here. You see you got this right there. If I shade in all that right there, that's basically how much storm energy you have to deal with. But if we go down here, we can take a look at the 0 to 3 kilometer cape here. And look at that right there. So if we kind of box in this right there, we see that we have in excess of 100 joules per kilogram of 0 to 3 kilometer cape. You have a lot of storm energy within that lowest environment. So it's going to allow for any spin at the surface is going to be brought vertically very quickly. If we take a look at our convective available potential energy, our storm energy across the whole atmosphere, it's very low. Quite lower than what you normally see even in other cold core events. And then also look at the surface conditions here in southwest Pennsylvania right there. You were 53 degrees with dew points in the upper 40s and you still managed to have tornadoes. That is like a big explanation of like, okay, this is probably getting close to a cold core event there. Now, let's look at our kind of our thermodynamic environment. Now let's go over to this part right here. Now this is called a hodograph, which basically tries to show the change of wind with height in the atmosphere. This is the lowest level of the atmosphere right there, and then it kind of extends up there. And there's kind of some interesting things you can do with hodographs. First of all, they can loosely show what a supercell is going to look like. So if you imagine the hook of a supercell kind of cuts in right there, and then the storm is kind of vented off to the southeast there. So if we go back, if I kind of show something real quick here, you can see that most of the tornado reports were in southwest Pennsylvania, and then they kind of get less as they drop off into western Maryland. And you can see that already here in southwest Pennsylvania, you do have a good, not a good, but you have a modest amount of low-level curvature right there. So see how it kind of, basically, the amount of, since it curves like that, the more curve you have, the more spin you have in the lower level of the atmosphere that you can get tornadoes. So you show that you do have a little bit there. It's not a lot, but again, when we have so much low-level storm energy, any low-level spin at the lowest levels of the atmosphere was able to be stretched vertically and become part of the rotating storm. But if we go a little bit further to the southeast, This was taken near Accident, Maryland, an hour later. This is again a wrap reanalysis sounding. But let's just focus on the photograph here. The spin there is very little low-level spin. I mean, again, this is, even if we go back to neither of these photographs look very indicative of tornadoes, but even less so in Western Maryland. Now, we can say that maybe it's possible that these were a little bit more curved. You can always say that's possible. This is just a model reanalysis, so it's possible it wasn't fully catching the small spatial scales that these tornadoes were interacting with. But really, you had shear, you had some shear, but very little low-level curvature here, there in Accident, Maryland, and yet you still saw tornadoes. And if we kind of go down there, you can see that you still had plenty of low-level capes. So what meager shear there was in the low levels was stretched in the vertical, and again, you still had dew points in the upper 40s, so you had very little storm energy to deal with. So this is a very interesting thing, and I did some research this past spring looking at different tornadoes in complex terrain, mountains. And I did find LaPinta et al., when they were looking at the Mechanicville, New York tornado in 1998, they found that sometimes that tornadoes could be fed by terrain influenced southerly flow, which basically inflow the warm air feeding into a storm. That terrain would help that. Bozart et al. Found that in the study of the Great Barrington, Massachusetts tornado, they found that there was a whole host of terrain influenced impacts on supercells, that the terrain influenced would actually enlarge the photograph. So it's possible that the photographs that we're looking at here are not truly representative of how much curvature you actually had of the winds at the lower levels. And this is just kind of a very interesting topic, and we'll never truly know, because we don't have the soundings right there. In Western Maryland, we didn't have a Doppler on wheels sitting there that was able to do all that. So we have very limited data. We can only use what we have. But still, it's possible that there was some terrain-induced impacts with this storm, because, by all accounts, it just doesn't really make sense of when it just completely duped weather forecasters. So let's take a look at the radar image here, if I can get it to go here. So this is a look at the radar image here from the Pittsburgh radar here, and I'll let it kind of loop back here. So a couple things to note right away is that on the left-hand side is what's called reflectivity, which basically measures how much rain is falling, or hail. On the right-hand side is what we call velocity, which measures rotation, basically winds to and from the radar. And if we look over here, you can see we have our supercell in question. It's moving off to the southeast there. And you remember when, if I can kind of go back here and look, this is actually this is a little bit better here. This is actually a video, so I can pause it. A little bit better quality, but remember how I showed the photograph, how it kind of looked like this, and it kind of vented off? Well, sure enough, look at it. There it is. You have your storm right there. That's where I'm kind of over dramatizing the hook, and then you're vented off to the southeast there. So if we go a little bit further in time, I'll switch back to the kind of the higher resolution GIF there. You can see you have your supercell is moving out of Uniontown. This was a long track producing all that swath of tornadoes. You can see it begins to weaken as it hits the mountains, but it still maintains its tornadic characteristics. Again, this was not tornado warned. And there's one feature. If we look at the left, we see the storm, but then look on the right here. There is your area of rotation right there as it pushes off to the southeast. That area where red and green are coming together, that shows where a wind is going away from the radar and where wind is coming towards the radar, and that shows rotation. So there's your area right there, here, and that couplet continues off to the southeast here. So you just basically had a long track supercell that was continually producing tornadoes, and it was just kind of able to continue off into western Maryland. You can see that by the time it starts beginning to interact with the eastern continental divide, you start seeing that it begins to weaken. It begins downsloping where air sinks as it drops off the eastern side of the mountains. So just a very interesting severe threat there, but it was able to do it in a very meager storm environment. So that's kind of all I have for this, but I did want to just basically provide this case study so that you all could maybe get a better understanding of how complex weather forecasts are, especially dealing with cold core events. Basically, you had a weather system that was able to do a lot with very little, and it showed. And it really duped weather forecasters, not to bash them, but it shows that we have a lot to learn. It's possible there was some terrain interactions that allowed for maybe a little bit more low-level spin. The case studies looked at, some talked about where there were basically terrain created these little boundaries of low-level spin that once you get a storm that moves over that, it's able to ingest that low-level spin and produce tornadoes. So I'm glad that there was no injuries or deaths with this tornado, because it really it didn't come with any warning, but it kind of moved over mainly rural areas. It did impact some homes, but it was overall very close. And we're still a lot of study. If you go back to another tornado outbreak in western Maryland was the June 2nd, 1998 outbreak, and that was actually my focus this past spring. And that was another event. That environment, whole-scale environment, was much more indicative of tornadoes, but you also had one particular storm that was able to produce an F4 in Frostburg, Maryland, which is off to the east of Accident, Maryland, and it was overcome downsloping. And so it shows that tornadoes in complex terrain, there's still a lot of research and a lot more stuff to be done. So I hope this case study has been helpful for you, and stay tuned.